In this installment of Introduction to Microcontrollers, we will focus on electric circuits. Let's look again at the microcontroller system. In this video, we'll focus on the circuit part of the system. A circuit is a looped path that allows electricity to continuously flow. Usually, an electric circuit has components in it, such as at least one power source, switches, lights, motors, speakers, and other devices that use electrical energy to do something. How do we define electricity? Electricity is the flow of charged particles, which can be electrons, ions, or other subatomic particles that carry charge. Electric current is a measure of flow rate, really how much electric charge is passing a specific point along a path. Current is measured in amperes, or amps for short. 1 ampere corresponds to a huge number of electrons, more than 6 times 10 to the 21st per second. 1 ampere is equal to 1 coulomb per second, where the coulomb is a measure of electric charge. We use the symbol I to represent current because André-Marie Ampère, a French physicist who did groundbreaking work in the study of electricity, first called current intensité du courant, or current intensity. So that's current. Now let's consider voltage. Voltage is the difference in electrical energy between two given locations. It's the work needed to move electric charge from one point to another. When work is done on the charge, it adds energy that can be used later. It's measured in volts. 1 volt is equal to 1 joule, a measure of energy, per coulomb, a measure of charge. Let's consider the circuits shown in this figure. Here, we want the energy provided by the battery to be dissipated in the light, causing it to turn on. However, a closed path is necessary for electric current to flow. Electric current shown here in the right-hand circuit is shown in such a way, the convention is that it flows from the positive terminal of the source, here, that's the battery, back through the negative terminal. Circuits can be composed of a variety of elements, some of which we'll discuss now. We want in particular to be familiar with the diagrams that are used, the figures that are used and inserted into circuit diagrams so we can recognize them. First, there are sources which provide power to the circuit. There are voltage sources which are drawn in circuit diagrams as shown. The plus and minus signs correspond to the positive and negative terminals of the voltage source. We expect a change of V volts across this element. When there is a single voltage source, as we see in the circuits we will be building, the current flows in the direction shown. As current flows through the voltage source, energy is added to the charged particles, and one specific type of voltage source is a battery, which is sometimes drawn using special notation. The positive and negative terminals of the battery are marked as shown, and the current direction follows the same convention as the other voltage source. The nominal voltage remains the same, at least in theory, regardless of the current flowing through the source. Besides voltage sources, there are also current sources. A current source provides energy to the rest of the circuit, so there is a voltage rise across the current source. Current is in the direction shown. The current I associated with the source is the same current I entering the source and leaving the source. So for sources, we expect the current to flow through the source, entering it into its negative terminal and exiting through its positive terminal. Besides sources, there are wires, and here's how they're drawn. For a wire, we assume zero change in voltage, that it's a lossless wire, that there's no dissipation of energy at all along the wire. It's idealized. I mean, in reality, there is loss, but It's very, very small typically, and for our purposes, it's fine to say that it's approximately 0. The current can flow in any direction. We just need to specify the direction. Next is the resistor. Here is its circuit symbol. The voltage change across it implies that energy is dissipated in the resistor. It's also called a load. We assume that the current enters the resistor through the positive terminal because it absorbs energy. Whereas sources, at least when you have a single source for a circuit, the source always provides energy. As is true for all the circuit elements shown here, the current that enters the resistor is the same as the current that exits it. Sources supply energy, resistors absorb, dissipate, or use energy. Now we want to talk about resistance. Resistance describes the relationship between the voltage and the current in a resistor. In a normal resistor, voltage is directly proportional to the current. The current of proportionality is called the resistance, and it is measured in ohms. Resistance is a measure of how difficult it is for charged particles to move through a given material, in this case, the resistor. And here again is a circuit diagram showing a resistor. As stated before, we expect there to be a voltage drop across a resistor as it uses energy, and current flows through the resistor, entering the positive terminal. The equation V is equal to Ri, which describes the relationship between voltage and current in a resistor, is known as Ohm's law. Now we'll consider fluid analogies. An electric circuit is analogous to a fluid system, where the electric current flowing through wires is like a fluid flowing through pipes. The voltage is like the pressure of the fluid. The power supply, which may be a voltage or a current source, is like a pump, and resistance is like a narrowing of a pipe. Now let's look at diodes. Here's one. This is a light-emitting diode. As noted before, one of the wires protruding from it is longer than the other. Some elements, like resistors, are bidirectional. That means the orientation in which they are placed in a circuit doesn't matter. They'll behave the same way either way. The orientation of a diode, on the other hand, determines its circuit behavior. The longer wire, is the anode, and the shorter one is the cathode. Current in a diode can flow only in one direction, entering the anode and exiting the cathode. This is the diode symbol seen on a circuit diagram. The anode and cathode ends are shown. The current must flow from the anode through to the cathode. No current can flow in the opposite direction. The circuit diagram actually helps us to remember the allowed direction of current flow. Kirchhoff's current law is one of the three major rules that is used to analyze circuits. Let's see how it works. Here we have three wires connected together. The junction is called a node. Let's say we have current I1 flowing in one branch towards the node, and that we have I2 flowing in another branch towards the node, and that we have I3 in the third branch flowing away from the node. Logically, we see, especially when considering current to be like a fluid, that I1 plus I2 is going to equal I3. We don't expect current to pool at the junction. According to conservation of energy, it's not going to be able to do that. More generally, the sum of currents entering a node must equal the sum of currents leaving that node, which is Kirchhoff's current law. Now here's an example of an application of Kirchhoff's current law. If we apply this rule, saying that the sum of the currents entering the node must equal the sum of the currents exiting a node, then in this case we can solve for the unknown current Ix. We see that the currents entering the node are 6 amps minus 1 amp and I sub x. And the currents leaving the node are 2 amps and 8 amps. And when we solve this equation algebraically, we find that Ix is going to equal 5 amps. Now let's look at Kirchhoff's voltage law. Let's say we have a circuit with a voltage source and a resistor connected together with wires. There is a current IA flowing through all elements, the same in all the wire. The current doesn't pull anywhere, so it's the same everywhere in this loop. As we move through the source, we experience a rise of V volts as the source supplies energy, and then as we pass through the resistor, there is a drop of lowercase v volts as the resistor uses energy. This means that capital V volts equals lowercase v volts. If instead we have this circuit where we can begin in the lower left corner and rise by passing through the voltage source by capital V volts, and then progress along the top wire from left to right in the direction of the current. And then as we move through R1, that resistor, there is a drop of lowercase v1 volts, followed by another drop of lowercase v2 volts. Getting back to the place we were at the bottom, we would see then that capital V volts is going to equal V1 plus V2. In general, according to Kirchhoff's voltage law, the sum of all the voltages around a closed circuit is going to equal 0. The idea being that the amount of energy, the potential energy, has to be the same at a given point, no matter how we reach that point. And this is what leads us to Kirchhoff's voltage law. So here's an example of how Kirchhoff's voltage law can be used to find an unknown voltage. If we have a source with a voltage of 15 volts and we know that the voltage across one of the resistors is 5 volts, then we can use this equation, capital V equals V1 plus V2, to solve for V2 actually. We see that V2 is going to equal capital V minus V1, and we can then insert the numerical values and find that V2 is going to be 10 volts. So Ohm's law, Kirchhoff's current law, and Kirchhoff's voltage law are the laws that we can use to solve circuits. So we'd like to now move on to building circuits, now that we have a basic understanding of how current and voltage work in these elements. So in order to build circuits, we're going to have to look at the breadboard. This is one of the components that we have in the microcontroller kit. The breadboard is a device used for prototyping electronic circuits that allows for easy connection of electronic components. We're not putting it together in any kind of permanent way, but it's a quick way to build circuits and test them out. So the idea is that each of the holes, we can insert a wire into the hole. We can insert a pin from the Arduino. In fact, we've already mounted the Arduino at one end of the breadboard with the connector at the top. And this means that the cable that we use to connect to the computer does not cross the breadboard at all. This leaves a lot of room on the breadboard for building circuits. So let's look at the different parts. So the part marked A, column IDs, we see that each vertical column in the prototyping area is labeled with a letter. That's helpful when we're trying to describe which column we're talking about. Okay. Then we look at B. B marks the positive terminal. All the holes next to the red or pink vertical stripe with a plus sign at the top and the bottom are connected to each other. These holes constitute a single junction or node. And this is where we would connect. Usually it's good practice to connect to the source that supplies electricity to this node, and then from there connect to other things that would be on the prototyping area. C marks what's called the non-conductive gap. I sometimes think of this as a canal. It's an indentation in the board. It's the middle section that divides the board into two unconnected sides. We have row IDs. On the boards that we have, they're only marked every 5 rows, but they're marked so that we can identify which row we're talking about. And they're marked with numbers as opposed to the letters that mark the column IDs. Then we have the negative terminal. There is a column on the far side, and it has a black or blue vertical stripe with a minus sign at the top and bottom, and all of those holes are connected to each other. These holes are used to ground the circuit. You'll notice that there are actually two negative terminal columns on this board. They are not connected to each other. You can choose to use one or both of them, but remember that they are not connected to each other unless we explicitly connect them. The same is true of the positive terminals. There are two columns that serve as positive terminals, and they, again, are not connected to each other. Then there are the connected rows. These are very important. You see that they're on both sides of the non-conductive gap. So when you see those 5 holes that are all in a row together, those constitute, in each row, those constitute a node. So anything that we connect into one of those holes, the 4 other holes are considered to be connected there. So if we connect 2 things in 2 holes in the same row, they are connected. Then there is what's called the prototyping area, which is pretty much the whole board. The center section of the board is the prototyping area. Any hole in the prototyping area can be referenced by a number-letter combination. So the hole that's marked there would be designated 28H. It's helpful to mark these holes because let's say we decide to build a circuit and then we're going to tear it down because we need to pack up and go do something else. It'd be nice to write down the locations of where we inserted the various components so that it'll help us to remember how to rebuild the circuit another time. So let's talk about how we're going to build a circuit. The one that we want to build is a diode circuit. This circuit is using the Nano and connecting it to a resistor and a diode. And the idea is that we want to connect the resistor diode sequence, this series combination, with pin 13. Now you may recall in looking at the blank sketch that this is the built-in LED pin. So the onboard LED that blinks, the LED marked L on top of your Nano, is connected to that D13 pin. And the sketch that we used, the blank sketch, specified that that was to be an output pin. So since that's an output pin, it means that when the voltage is high, when we set it to be high, it means that there's a high voltage there, and that gives energy that can be used by this circuit to have current flow through the resistor and the diode, and it will turn the diode on. Okay, and then the current will flow back to ground here. Okay, and then the idea is that when the voltage is high, according to the sketch, the light should be on, and when the voltage is low, the light will be off. Okay, so that's how that's going to work. So we would like to build this circuit. It will use the blank circuit in an extended way from how we used it before. And that means that we need to identify the pins that we want to connect wires and then the resistor and the diode to. So it turns out that this ground that's marked in the circuit diagram on the left, we can find a ground pin on the Nano. So I've oriented the picture so that the connector is at the top, and this is how it should appear on your breadboard. This will make it a little easier to do the connection. The ground pin on the Nano is marked GND. There are actually 2 ground pins on your Nano, and you can use either one. The ground pin that's marked here is the one that's on the left side of the Nano when you have the connector at the top. The other ground pin is on the other side of the Nano. The D13 pin is also on the left side. It's the topmost pin. Okay, so you need to find those 2 pins, and then the holes that are in the breadboard that are just to the left of these 2 pins are places that you can connect wires, and then you'll be connecting that pin to other things. So what you want to do is find a wire, probably a long one that's got male ends. Insert one of the ends into one of the holes that's just to the left of pin D13, and then you want to connect the other end to a hole that is in a row that is below the bottom end of the Nano, because all the rows that are immediately next to the Nano on both sides, they connect to pins, and the only pins we want to connect to for this circuit are pin D13 and the ground pin. Okay, so just take a wire that's long enough that you can connect it to D13 and then to a pin lower down. And then once you've selected a row, you want to find a 220 ohm resistor. It's one of the fixed resistors, one of the striped cylindrical resistors that you have in your kit. We will talk about how to identify the resistors with the striping at a later session. But for now, what you want to do is look in your kit, and then you'll see that the resistors are bundled together with brown tape at the top, and you want to find the set of resistors that has the marking 220R. And all of those resistors are 220 ohm resistors. So you want to select one of those, and you want to insert one end of that resistor into a hole that's in the same row as the wire that connects D13 down to a lower hole. Okay, and then once you've done that, you want to insert the other end of the 220 ohm resistor into yet another row. Okay, and then you want to pick a diode. Choose one of the diodes from your kit, and you want to connect that one to the lower end of the resistor. You choose a hole that is immediately in the same row as the lower end of the resistor. Put the long leg of the diode in, and then put the short leg of the diode into yet another row. Okay, so let's say, for example, you connect your wire that's at D13 down to, say, row 22. Okay, you pick a hole in row 22, one of the A through E holes, let's say. You put your wire into 22A. Then you want to stick one end of the resistor into, say, 22C. So it's in the same row as the wire, row 22. Then you take the other end of the resistor, and let's say you put it into row 24, say 24C. Okay, so it's in a separate row. Then you take the anode leg, the long leg of the diode, and you insert it into one of the holes in row 24. So maybe you'd pick hole D. Okay, so then you have a resistor leg in 24 and a diode leg in 24, and you put the other diode leg in say row 25. It doesn't matter which hole you pick. Let's say you pick 25D. Okay, the last thing you want to connect is a wire, the wire that's on the lower end of the diode. You want to run that wire from some hole in row 25, let's say 25E, all the way back up to a pin, a hole that's just to the left of the ground pin. I hope that wasn't too confusing. It'd be hard for me to show you the board, but I'm trying to give examples of how you could make this work. So the example that I used, we'd go from D13, just to the left of it, to row 22 to row 24, row 24 to row 25, and then row 25 back up to ground. Okay, and then the idea being that you just pick two holes in row 22 and make sure you put the ends of the wire and the resistor, and then you pick two holes in row 24 and you put the ends of the resistor and the diode, and then you pick two holes in row 25 and you put the short leg of the diode in with one end of the wire, and then you lead the wire up to ground. Okay, so then you should be connected, and then once you've checked to make sure that you did it correctly, then you can connect it to power. And what you should see is you should see the diode light blinking. If you've done it correctly, you should have the power light glowing on top of the Nano. You should have light L blinking as it was doing before, that onboard LED that blinks, okay? And then you should also see the diode blinking at the same rate. All right, now we would like to make some measurements. Okay, we'd like to measure the voltage across the resistor. We'd like to measure the voltage across the diode. And we would like to, from that, figure out what the voltage across D13 and ground would be. Okay, and so we should be able to calculate that with not need to measure it, because we can use Kirchhoff's voltage law to find out what that is. Basically, the nano serves as the source, and then the resistor and the diode are the loads. So we can calculate it. And we'd also like to measure the current that's flowing in this loop. Now, the values that we get for these different components, the various voltages, actually the one that's up here for between the D13 and ground should be the same no matter what we connect it to. But the voltage across the resistor and across the diode, how it's divided here between them, is going to depend on our selection of diode. The voltage across the diode does depend somewhat on what color we choose. So that's something that I'd like you to note when you're doing this. But then you may ask, well, how am I supposed to make these measurements? So now we need to talk about how to make measurements. In your kit, you have a multimeter. Okay, the multimeter has different settings, and meter means measurement, and the multi-part is tells you that you can make different kinds of measurements. And the first one we want to look at is voltage. So when you find your multimeter, the first thing you want to make sure of is that it's in the off position, okay, which means that this yellow mark up here, that the dial is turned to that. But we'd like to use it as a voltmeter first. You need to put your leads in, the black lead into the COM port and the red lead into the center port. You need to make sure that you press them in firmly so that they're fully inserted into these ports. So we use the dial on this multimeter to go towards the DC voltage position, okay, direct current. And that's the portion of the dial that's marked with the V, and then it has a horizontal line with 3 dots under it. Okay, that's the part that we will be using in this class. And then we want to look at the different settings within this range. We use the dial and the multimeter to select the type of electrical measurement that we want to make and what range we have. And generally speaking, we want to use the range that will give the most precision without going over the maximum value. So in this image, the settings shown are for measuring voltage with direct current. Voltage is indicated by the capital V. Direct current is indicated by the symbol that has the 3 straight lines over the dashes. The alternating current setting is one that we're not going to be using in this course. So for DC voltage, we have 5 different possible ranges. We have 200 millivolts, we have 2000 millivolts, which is the same as 2 volts, 20 volts, 200 volts, and 600 volts. These numbers represent the maximum voltage that can be measured on each setting. So for example, to measure the actual voltage of a 9-volt battery, we can't use the 2-volt setting or the 200 millivolt setting because the 9-volt battery has a voltage that is higher than the range of those settings. If we do, then a 1 will appear on the display for the multimeter, indicating that the voltage is out of range. So the appropriate voltage for us to use would be the 20-volt range. So in order to measure the voltage, we actually take the test leads and place them at the endpoints of the component for which we'd like to measure the voltage. So it's when you find voltage, it's always relative. It's the voltage is between 2 points. These are the test leads as marked, and they're connected to probes that end with metal tips. Now, when we want to measure current, it's a little more complicated. In this image, the settings for measuring currents are as shown. The multimeter has 200 microamp setting. It has a 2 milliamp setting, a 20 milliamp setting, a 200 milliamp setting, and a 10 amp setting. For measuring current less than 200 milliamps, we'd plug the red test lead into the volt-ohm milliamp port, which is the center port. Then we turn the dial to one of the milliamp settings. For measuring current up to 10 amps, the red test lead must be plugged into the 10 ADC port, which is the one on the left. Okay, so the red test lead would have to go over there. Then we would turn the dial to the 10 amp setting. We should not need to use the 10 amp setting or port for this course. But generally speaking, if we don't know the current, then we want to begin with that setting. Here we expect the currents to be accommodated by the 20 milliamp setting in general. But typically we want to choose the setting that is the smallest one that we can get away with, because then we'll have the highest possible precision. To measure current in a circuit, the multimeter must be inserted into the circuit. In other words, it must become part of the circuit. This is different from measuring voltage or resistance that can be measured across a component in the circuit. You'll have a chance to do that a little later when you start building circuits. So now let's talk about the assignment. What I would like you to do is build the circuit and measure the voltages VR and VD. And then I would like you to report what they are and also the color of the diode that you have in your circuit. And then I would like you to use Kirchhoff's voltage law to calculate Vs. I would also like you to measure I. So in order to measure the voltages, you're going to have to use the voltmeter aspect or the voltmeter functionality of the multimeter, and then to measure the current, it will be the ammeter functionality. And then I would like you to change the diode that you have in your circuit to a different colored diode. Note the brightness of the light. Is it brighter or dimmer than it was before? And then go ahead and repeat the steps measuring the voltages and calculating the current, and record those. And then I would like you to change the circuit so that instead of having one diode, you have two in a row, two connected, one after the other in a chain. So you'd have the sequence of resistor directly followed by diode, directly followed by another diode. Please record the colors and the LED brightness. Compare them to the cases when you had just a single diode. One of the things that you may want to do to make this a little bit easier is to change your blink sketch so that the on portion of the cycle is a lot longer. You might want to make it 3 seconds or 5 seconds long, or maybe even longer, so that you can get an accurate measurement. Because if you have your blink sketch set so that the diode is turning on and off every second, you're going to find it a little tricky to measure voltages because they're going to keep changing. Same for the current. So this is what I would like you to do for the assignment, and I will put further instructions on how to complete it on Canvas.